Gets it back.
Hello,
Chipping it
and
forward.
welcome to lecture
Overlapping
number
run
3
is
in
there!
calculus-based
And it's
physics.
netted by Deuce!
Today we will be discussing
Dempsey with his
motion in more than
31st,
one
and
dimension.
the U.S. with a 1-0
After this lecture, we
lead.
will be able to
Absolutely an
describe the motion of
international
things
class
like a
goal.
soccer
The
ball being
finish
passed
is
around the pitch,
exquisite.
or even the trajectory of the ball as it flies through the air. We'll focus in on two particular types of motion in 2 dimensions: projectile motion near the surface of the Earth, and motion on circular paths. Let's start by seeing how motion in 2 dimensions compares to motion in 1 dimension. It turns out it's quite similar. We just have to redefine our kinematic variables slightly. We define position in 2 or 3 dimensions in much the same way as we did in 1 dimension. The position vector points from a reference point, typically the origin, to the location of an object. The only difference is that we now call the position vector r, and that it can have x, y, or z components, as opposed to motion in 1 dimension where we didn't have to worry about vector components. Finally, the displacement is defined as the difference between initial and final positions, just as it was in 1 dimension. Average velocity has the exact same definition as it did in 1 dimension. We just have a new variable name for position. It's simply the object's displacement divided by the elapsed time. All we've done is changed the name of the position variable from x to r. The average velocity in general is a vector, and that can have x, y, or z components depending on whether you're working in 2 dimensions or if you're working in 3 dimensions. The instantaneous velocity is again just the first derivative of position. This is the velocity of an object at a particular instant in time in 2 or 3 dimensions. In order to compute the components of the velocity, we can just compute the derivative of the x, y, and z components of the position separately. Here, x, y, and z are the positions of an object in the x, y, and z directions respectively. Next, acceleration is handled a bit differently in 2 or 3 dimensions compared to 1 dimension. However, in general, the definition is the same. It describes how an object's velocity is changing with time. Now, since velocity is a vector, there are 2 ways in which one can accelerate. First, by changing the magnitude of the vector. This means changing your speed, speeding up or slowing down, or by changing the direction of motion, in other words, turning. Both of these result in a different velocity vector. Shown here is a car that is turning and slowing down at the same time. Therefore, the second velocity vector, v2, has a smaller magnitude than v1 and is pointing in a different direction. The average acceleration is given by the change in an object's velocity over the elapsed time, same as in 1 dimension. The direction of the acceleration vector always points in the same direction as the change in velocity. In this case, shown here, the velocity is directed towards the center of this curved path. If we look at any of the velocity vectors we've just drawn, they always point tangent to the path taken by the object. We also just saw that the acceleration vector always points in the direction of the change in velocity. This translates to the acceleration vector always pointing toward the interior or concave side of the curved path. Just like with the instantaneous velocity, the instantaneous acceleration will have components, each of which can be computed by just calculating the derivative of the x, y, and z components of velocity. Now, since the definitions of the kinematic variables has not changed from one dimension to 2 or 3, the 4 kinematic equations that we derived in lecture number 2 will also not change. The only slight difference is that each of the terms in the equations are vectors, as shown here. Now, the fact that we're in 2 or 3 dimensions complicates things a bit. Whenever we're doing math with vectors, we always have to break them into their respective components. This means that we will have a set of 4 kinematic equations for both the x and y directions, for a total of 8 equations. More on these later. Note that if we were working in 3 dimensions, we would have another set of 4 equations that look exactly the same, just with subscripts z. For now, we're going to work in 2 dimensions. Before moving on, let's look at the components of acceleration a little closer. Suppose we have an object moving around a curved path as shown here. If this object is speeding up while turning, the acceleration will be represented by the orange vector. Note that the black line labeled normal at P is simply just a line that is perpendicular to the path of the object. Normal is just a fancy way of saying perpendicular to. Note that the acceleration is pointing toward the inside of the curve as we stated before. Also note that the acceleration can be broken down into 2 components. A component perpendicular to the path, which we will refer to as A perpendicular, and a component parallel to the path, which we will refer to as A parallel. The perpendicular component of the acceleration causes the direction of the velocity vector to change. It does not affect the magnitude of the velocity vector. The parallel component of the acceleration is what causes the magnitude of velocity to change. In other words, the parallel component of the velocity acts to slow the object down or speed it up. Consider an object moving on the same curved path as before. Now the object is going to be slowing down as it turns. This time, the acceleration vector is in a slightly different direction. It's still directed toward the interior of the curve. It still has a component that is perpendicular to the velocity, which again we call A perpendicular. And it still has a component parallel to the velocity vector, or in this case, it's actually anti-parallel, pointed in the opposite direction as the velocity vector. Lastly, suppose we have an object moving on the same curved path, but it is moving at a constant speed. In this scenario, the acceleration is still pointed toward the interior of the curve. The acceleration has a component perpendicular to the velocity, A perpendicular, but this time there is no parallel component of the acceleration. We know this must be the case since we assumed that the object was moving at a constant speed, and the only component responsible for changing the speed is the parallel component of the acceleration. This is a special type of motion called uniform circular motion. This occurs when an object is moving on a circular path at a constant speed. Note that even though the object is moving at a constant speed, it is still accelerating by virtue of the velocity vector turning as the object moves around the circular path. A special case of two-dimensional motion is the motion of projectiles near the surface of the Earth. Of course, in reality, projectiles like the baseball in this video move in 3 dimensions, but we can explain this motion assuming only 2 dimensions, using the principles of motion described previously in this lecture, as well as in lecture number 2. First off, what is a projectile? A projectile is any object that is given some initial velocity that then follows a path determined only by gravity and air resistance. Just as we did with freely falling bodies in lecture number 2, we're going to ignore the effects of air resistance for the time being. If we do this, the path of the projectile is parabolic, as shown here. Consider 2 balls that are being dropped from a certain height. The red ball is released straight downwards from rest, whereas the yellow ball is given some initial horizontal velocity to the right. After being released, both balls are only being acted upon by gravity, so by definition, they are both projectiles. If you compare their vertical positions as they fall, you'll notice that they are falling at the same rate. This rate is the acceleration due to gravity, minus 9.8 meters per second squared. But the yellow ball is moving in both the horizontal and vertical directions. What about its acceleration in the horizontal direction? Since gravity only acts in the vertical direction, downward, and there is no air resistance, there is no acceleration in the horizontal direction for the yellow ball. This will simplify the math greatly in just a second. Projectile motion is really an example of 2 types of motion occurring simultaneously. In the horizontal direction, the projectile is moving at a constant speed, since the acceleration is equal to 0. However, in the y direction, the acceleration is minus 9.8 meters per second squared. So it is undergoing uniform acceleration in the vertical direction. This can be seen by looking at how the vertical and horizontal components of the velocity change as a projectile moves along its trajectory. Notice that the vertical components are getting smaller in magnitude as they travel up to the top of the path, and then flip direction and get larger as they travel back down. Notice also that the magnitude of the horizontal components never change, because there is no acceleration in the x direction. The x and y components of the velocity vector can be computed just like any other vector using right triangle trigonometry, SOHCAHTOA. Now, back to the equations that describe this motion. Previously, for motion in 2 dimensions, we had 8 kinematic equations, 4 for each dimension. Fortunately, for projectile motion, these simplify greatly. First, in the x direction, the acceleration is equal to 0, which amounts to saying that we have motion at constant velocity. The only equation that describes motion at constant velocity is distance equals rate times time, or in this case, delta x equals v initial x times time. Finally, the equations in the y direction are only edited slightly by changing a sub y with negative g. So we've reduced our problem of projectile motion from 8 equations to 5. These kinematic equations fully describe the parabolic trajectory of any projectile. Let's see how this works. Suppose we have an object launched at a velocity of 20 meters per second at an angle of 25 degrees upward from the horizontal. We'd like to know what is the maximum height reached by the object. What is the total flight time of the object? What is the horizontal range? And what is the magnitude of the velocity just before it hits the ground? Okay, what is the maximum height reached by the object? We aren't given much information in the problem, only the magnitude and direction of the initial velocity. Now remember, since we are working in 2 dimensions, our equations are split between the x and y directions. Therefore, the first thing we need to do is determine the x and y components of the initial velocity. Here we've used the standard equations for computing x and y components. Now, what else do we know that could be relevant to determining the maximum height? Think back to freefall. What is true about the motion of an object when it is at its maximum height? Hopefully, you remember that its vertical motion stops when it is located at the maximum height of its trajectory. Therefore, if we treat this location as its final position, we can set the final velocity equal to 0. Then we can make use of the 4th kinematic equation to determine the vertical displacement, which corresponds to the maximum height reached in this case. Solving this equation for delta y gives us a maximum height of 3.64 meters, which is approximately 10 feet. You should double check my math on this one, on all of these problems. My calculator skills are not the best. Now, how long is it in the air? Or in other words, what is the total flight time of the projectile? In order to solve this, what could you say about the vertical displacement of the ball over the course of its entire trajectory? Since it starts and stops at the same height, the ground, the vertical displacement must be 0. Now we can make use of the 3rd kinematic equation to determine the time of flight. Setting delta y equal to 0, we can rearrange and cancel one of the t's on both sides. Then the time of flight is 1.72 seconds. Note here, when I plug in for ay, we're plugging in ay equals minus 9.8. So the minus signs cancel here. Finally, what is the horizontal range of the object? We should note that the horizontal range corresponds to how far the object travels horizontally. Since there is only one equation that describes horizontal motion, the displacement in the x direction is given by delta x equals v initial in the x direction times t. Plugging in what we know, our horizontal range should be 31.18 meters. Finally, what is the magnitude of the velocity just before it hits the ground? Well, we already computed the initial x and y components of the velocity. Since there is no acceleration in the x direction, the x component of the final velocity must be the same as the x component of the initial velocity. So v final x is equal to 18.313 meters per second. We can then use the initial y component of the velocity along with our calculated time of flight to determine the final y component of the velocity, which I get to be minus 8.45 meters per second, which makes sense because it is negative, indicating that it is falling. Then the final velocity is determined using Pythagorean theorem. We have the x and y components of the final velocity, so plugging them into the Pythagorean theorem gives us the magnitude. Note that the final velocity is not 0. Remember, we mentioned in class that the final velocity is the velocity that the object would have if the ground were not there. Okay, now we've seen how to describe the acceleration vector if an object is moving on a circular path at a constant speed. But let's dig a little deeper and put some equations to this. Eventually, we'll be able to describe things like the motion of planets, which move on approximately circular paths around the sun. First, recall that any object moving on a circular path at a constant speed is undergoing a special type of motion called uniform circular motion. Here the velocity vector is always pointed tangent to the path, and the acceleration vector is directed toward the center of the circle, perpendicular to the velocity vector. This acceleration can be calculated using this equation, a equals v squared over r, where r is the radius of the circular path, and v is the constant velocity taken by the object. This acceleration, since it is always pointed toward the center of the circle, is called the centripetal acceleration. Now, suppose an object traverses a circular path of radius r in a time capital T. We now know that the acceleration of this object is given by v squared over r. And we can compute the speed with which this object is traversing the path, since speed is just distance over time. And the distance traveled is simply the circumference of the circle, 2 pi r. Then the speed should be 2 pi r over t, the amount of time that it takes to go around the circle once. Plugging this into the acceleration, we get a equals 4 pi squared r over t squared. These equations will be extremely useful once we get to the topic of centripetal forces. This concludes our lecture on 2 and 3D motion. Here's a summary of the major points to take away from the lecture.